All right, well, hello everyone. Thanks for coming to our, I guess this is our third talk this quarter. We've got another one next week and then a few more as well. But today it's my pleasure to welcome Professor Lucas Meza to our seminar today. Lucas is an assistant professor here in mechanical engineering. He joined us in January 2019, so it's been about a year and a few since he's been here at UW and has seen quite a lot in his time. Prior to coming to UW, I'll start from the beginning with him. He did his undergraduate degree at UCLA. He then went on to do his master's and PhD at Caltech. He was working with Julia Greer, which is part of the topic he'll talk about today, I imagine. He then also spent a year at the University of Cambridge in the UK doing a postdoc with Vikram Deshpande. And that was working on some composite computational modeling. Here at UW, Lucas has an active lab. He's been leading some of our work in the nanoscale mechanics. His work has actually been well published. His publication record is quite phenomenal. He's got a publication in Science, a publication in PNAS, and a publication in Nature Materials, amongst a bunch of other additional high-quality journals as well. I was happy to have him present for us today. And again, just for our format, if you guys have questions, please feel free to save those until the end of the seminar. We'll do the Q&A. But if you want, you can go ahead and use the chat feature to ask your questions, and then we can field those questions, or you guys can go ahead and field them, ask your questions yourself. But without further ado, I'll let Lucas start, and thank you so much.
Yeah, thanks for having me. I'm really excited to be here talking to you all today about some of my work in micro and nano architected materials. So the talk, the general structure, I'll go through some of the background and what we're interested in studying, why we work on these materials to begin with. I'll talk through some of the work that I had done, primarily my work at Caltech. I won't go too much into what I had done at Cambridge, and then I'll tie that into what we're working on today and the types of problems we're interested in and the types of problems we're trying to solve. So, getting started, I have, my title is The Extreme Mechanics of Micro and Nano-Architected Materials. So there's probably a couple of questions that you have from the title. So first off, what is an extreme mechanical property? What is a nano-architected material or micro-architected material? And how do we make new extreme materials? So the way that I think about problems is generally I study the mechanics of materials or other material properties, and I try to engineer materials to have better properties. But in order to do that, first we need to ask the question, what is an extreme material property? And to help answer that question, we need to look at material property spaces. So this is an Ashby plot. Some of you may have seen this before in some form or other. This is strength versus density. So here we have, there's a lot of stuff going on. I'll try to break it down. Heavy, strong stuff, ceramics, metals up here at the top right. Lighter, weaker stuff, polymers, elastomers here in the middle, and then foams, very lightweight, but not as high strength. This green belt was natural materials, so wood and leather. And you'll notice here, there's a theoretical maximum. So this theoretical maximum generally is dictated by, it's a Voigt bound, taking the strongest material that would exist. So say a diamond or carbon nanotubes, graphene, something like that, and drawing a linear line from that. But you notice that there's a whole bunch of white space out here. So when I had started my PhD, this is kind of what the material property space looked like. We said, all right, there's all this empty space here. We could make very lightweight stuff. We could make medium weight stuff that's stronger, medium weight stuff that's stiffer. And the question was, how do we do that? And the answer that I'm going to give you is we use architecture and we use nanomaterials. So my intro is going to go through those two ideas and where we see it, both in engineering, how we do it, and then why we're doing it. So to start off, architecture. So architecture is something that's very common in the world around us. So there's different forms of architected materials that can exist, different shapes that you can have things take on. These are things that you're probably very familiar with, even though you may not be, it may not make you immediately think of an architected material. So here are stochastic materials you probably have sitting on your kitchen counter. It's a sponge, which has porosity to make it squishable and water absorbent. Layered materials you're probably wearing on your feet right now, maybe not because you're all at home and who wears shoes at home, but you have multiple layers of the shoes that give it a certain compliance, to give it a certain squishiness to make it comfortable to walk. Lattice materials, anytime you get a box from Amazon or wherever, the corrugation here in the cardboard is what allows that paper material to then be stiff in bending and then strong axially. So you have this corrugated plate that you're using the corrugation to give you some new property. And then fiber materials, you're definitely all wearing. Our cloth material, the fabric that we wear every day is actually a woven fiber. So very rarely do we wear monolithic sheets of something on top of us. It's actually very small fibers that have been woven together. And the pattern of the weave and the architecture of the weave is what gives it properties. That extends into carbon fiber composites and other types of fiber composites, ropes or fiber composites. So architecture in engineering and in the world around us is very common. And that's kind of our starting point for when we think about architected materials, is we want to use some of these concepts of architecture now to design better materials. So in recent years, so architecture has been used kind of all throughout human history, going all the way back. The earliest example was probably straw and mud brick reinforced houses thousands of years ago. In recent years, we've been able to, there's been a set of fabrication techniques that have really allowed us to scale down how we can introduce controlled architecture into materials. So one of the earliest examples is self-propagating photopolymer waveguides, which they used to create these sort of three-dimensional lattice materials. You can see the unit cells here on the order of about 1 millimeter. And then they used that, they created a polymer structure, coated it in metal, hollowed it out, and made what was, I think for 3 or 4 months, the world's lightest material. There's a fun picture of it sitting on a dandelion. This used UV light shown through a mask to create these sort of fibers. So it wasn't hugely versatile, but it was a scalable technique. And I think this was out of HRL Laboratories. They still have some work going on with it now. Around the same time, there was so most of you are probably familiar to some degree with stereolithography. So like a Form 2 3D printer uses stereolithography. Around the same time as this work was coming out, people were working on microstereolithography, so taking phase masks and putting them through projection lenses to make very small features, small featured structures. So now we could create structures with the same complexity, but with an arbitrary architecture. So here, this is a hierarchical lattice, which I'll talk about a little bit later in my talk. But now with similar features to this, there's self-assembly methods, block copolymer self-assembly, where you can get sort of different self-assembled architectures. This is a gyroid made from block copolymer self-assembly, where you can get features now that are tens or sub-10 nanometers sometimes, generally in a polymer. The technique that I use, that I still use here pretty heavily, is direct laser writing, or 2-photon lithography direct laser writing, where we take an infrared laser, shine it into a photopolymer, and we're able to make structures that are smaller than these techniques are able to do, not quite as small as a self-assembled structure or as block copolymer, but we're able to introduce an incredible degree of complexity into something at near fundamental material length scales. So what's the point of that? Why do we want to make things so small? Well, it turns out smaller is sometimes better. Smaller is more interesting. So this was a lot of the work that my former group, my PhD advisor Julia, had done during her PhD. When you take single crystalline metals and you make them smaller, you get a statistical increase in strength due to a range of effects. But basically, as you reduce this size, your strength gets stronger and stronger kind of exponentially. So if you're able to make something that's 10, 20 nanometers in diameter, you get near the theoretical strength of the material. You can get, for intrinsically brittle materials at the macro scale, you can actually have them become ductile at the nanoscale. So I don't know how many of you are familiar with metallic glasses, but it's an amorphous metal material that is generally fairly strong but brittle at the macro scale. You can actually get to length scales where you can suppress that brittle shear band location, and you can get some ductility into your intrinsically brittle material. That size isn't always good. If you take a nanocrystalline material, adding the free surface there actually allows grain boundaries to slide out, so you get smaller is weaker. So size matters and nano architecture matters. Most of the work that I had done actually focused on ceramics. So ceramics, this is the four bar buckling of a top end of a lattice structure. We were able to find that this had near theoretical strength of the intrinsic material. And this was enabled basically because ceramics fail at flaws or voids. When you reduce the material past a certain size, you physically can't have a flaw larger than a certain size. So statistically, you get this increase in strength based on Weibull statistics up until the point where you get near that theoretical limiting strength. This coincidentally was confirmed or validated a couple years later experimentally, where here there was this kind of interesting push to pull test where if you look, here's bulk alumina, mesoscale alumina, nanoscale alumina, you have that kind of statistical increase in strength with size. And when you get down to features that are about 20 to 30 nanometers, that's where you get kind of that theoretical limit strength of the material, which is the strength of the atoms ripping apart. So nanomaterials are interesting, and they exist everywhere in the world around us, but the question is, how do we use them? And so we wanted to, now we're trying to use this idea of architecture to couple in nanomaterials into our mechanical properties. That architecture now, so now once we have nanomaterials, we have to decide how we want to shape them. So there's a whole bunch of different ways we can create structures with different shapes. A lot of the work I had done early on was on lattice structures. So here, there's this kind of classical idea of bending versus stretching architectures, where here, this sort of octet truss would carry load in tension and compression and carry load more optimally than this tetrachedecahedron, which carries load primarily in bending. It turns out to be a little bit more complicated than that, which I'll talk about later in the talk. In general, though, people have found that lattices don't scale optimally. And actually, if you go to a closed cell architecture, you can get better mechanical performance. Here you can see lattice architectures versus normal or closed cell architectures. Even stochastic closed cell architectures generally perform better than lattices because walls are better at carrying load than beams. There's other reasons why that isn't necessarily ideal, and I'll talk about that also later in the talk. And then introducing hierarchy into our geometry. So now that we can make whatever shapes and architectures we want, we can start introducing structures at different length scales to feasibly get different properties. So I could combine a bending structure at a small length scale and a stretching structure at a larger length scale, and a tough or a negative Poisson's ratio at another level. And we can do that all in our design. So we can design these different structures at different levels with different architecture to bestow different properties. And where we see this most dominantly, so in the engineering world, we're just starting to scratch the surface of this, but a lot of our inspiration actually comes from natural materials. So if you look at trabecular bone radiolarians, these sea creatures, sea protozoa, or Euclactella sponge, which is one of my favorite creatures. It's also a stellaceous sea sponge. And you look down at the small scale, these are built up fundamentally at the nanoscale of these nanoscale constituents that are organized into some sort of architecture that are organized into another architecture at another length scale up, another, and so on. So here, this Euclactella is very interesting, or a really good example of that, because you have, at the smallest level, you have these tens of nanometer thick brittle sheets that are organized into a core shell composite with a polymer interlayer between them. Those are woven together into a structure, which are then woven together into a structure, which are then woven together into a structure across 4 or 5 orders of length scale, orders of magnitude. So it's this incredibly complicated structure that's designed from the nanoscale. and most natural materials have this sort of architecture built into them. It's just the ductile, you can see it pretty easily, whereas bone, it may not be as immediately apparent. What have we gotten so far? So let's go back to our Ashby plot, again, strength versus density. If we look at what some of those fabrication techniques have bought us, it's been able to extend that material property space. So here, we've been able to make things that are fairly heavy and very, very strong. This is amorphous carbon, which I'll talk about later. We can make lightweight materials that are as light as wood, but as strong as a steel. We can make ultra lightweight materials, which I'll also talk about later in the talk. We can make fully dense materials that are actually stronger than their base materials. So this is a porous copper, which was 60% dense and still had a higher strength than the actual bulk copper that it was made of. And that's because of those material size effects that I had been talking about earlier. So there's a whole bunch of interesting mechanical properties that we've been able to get, but this is only one narrow slice of the material property space. So this is strength versus density. There's a whole metamaterial property space that we can start to explore with these fabrication techniques, which isn't necessarily what I have focused on, but what there are a lot of people actively working on. So here we have oxidic materials, or negative Poisson's ratio materials where when you push on them, they contract, and when you pull on them, they expand. Pentamode materials, which are, it's a meta fluid. So if you think of water, water has a bulk stiffness, but no shear stiffness. You can flow water, but you can't compress it. Here you can create a solid material that actually has almost that property. It has some bulk stiffness, but it has a very low shear stiffness. And it turns out that's interesting for cloaking. You can create properties, or you can create materials with negative effective properties. So you can create these sort of mass damper systems, you get negative effective density or bulk modulus, primarily for wave propagation, which are very interesting. There's other non-mechanical properties as well. So this is some work out of Caltech that we had collaborated with Austin Minich on over there. He's a professor at Caltech on ultra low thermal conductivity materials. So it turns out when you start to make these ultra lightweight materials, you get ultra low thermal conductivity because there's nothing there to conduct the heat. So if you look at materials like aerogels, that's what aerogels do. But aerogels have this kind of stochastic architecture. They form randomly in whatever chamber you use to make them. And if you take effectively the same amount of material, but you intelligently architect it, you can get orders of magnitude better stiffness performance than you do with an aerogel. And this has applications, for example, as space shuttle tiles, where you can create something that's ultra low thermal conductivity, that's shielding, that's crack proof. And that's really what we're trying to go for with these. So this was a numerical study. They were able to validate that experimentally, some of those properties a couple years later. So I'll come back to this point later on in the talk. So now I'm going to talk a little bit about what I had actually worked on prior to coming here. So, or what my PhD work had been on. So a lot of the fabrication that we do is based around two-photon lithography. It's not necessarily a technique that I'm married to, but it's a useful prototyping tool. So effectively what we have, it's a nano 3D printer. You shine infrared light into your material. Infrared light alone isn't enough to cross-link the material. So anywhere the red light shines doesn't cross-link, it just stays a gel until you get to a very narrow focal point. And here, this narrow focal point, you have a statistical likelihood of getting 2 infrared photons absorbed. So those 2 infrared photons have the same energy as 1 UV photon, which most of these photoresists are designed to cross-link using. And so you only get cross-linking at that focal point. And so what this looks like, there's actually a couple different writing modes you can use. Here, you can actually write fully 3-dimensionally. So you're not limited to layer by layer writing. You can see there's a piezo stage that this is attached to, and it's writing these sort of octahedrons fully in space. Or you can do a layer by layer writing, which is generally faster writing, but then you have the stair-stepping phenomena or stair-stepping problem that you get with most 3D printers. At the end of this, you end up with a photopolymer, or a polymer structure. So that polymer alone has some interesting properties, but most of the time we use it as a scaffold. So we take that polymer structure and we do something to it. So in my PhD work, it involved using thin films to coat it. we're still doing some of that here, but we're also using pyrolysis to turn it into different materials. So here, that coating process, you would take a polymer, you use a thin film deposition technique such as atomic layer deposition to coat it with a thin layer of something, in this case aluminum oxide, because you can ALD any material as long as it's aluminum oxide. We take that aluminum oxide, use a focused ion beam to just narrowly expose the edge of the material, use an oxygen plasma to burn it out, and we end up with a hollow structure. So I'll show a few videos now on these hollow alumina lattices, hollow alumina nanolattices, and what their properties are. But here, dimensionally, we can control the thickness of ALD effectively to the nano level, to the atomic level. So we can get 10 or sub 5 nanometer thin films of aluminum oxide, which is effectively 15 to 30 atoms across. So we're really getting down to the scale where we're controlling the atomic organization of these structures. Here, this is the structure that we actually make. This is an SEM image. You can see the trench marks here on the side. That's the fib mark from exposing this. This, you can see the scale bar at the bottom is 20 microns. This whole thing is about 50 microns across. As a reference, the thickness of a standard piece of computer paper is about 100 microns. The diameter of a human hair is about 50 to 80 microns, depending on whose hair it is. So we're creating structures that are engineered at a level where these effectively look like specks of dust on a chip. So we can't actually touch most of them. We have to use fancy SEMs and nano manipulators to actually move these things around and test them. But that's why it's interesting science. So 50 microns total structure. These are built with unit cells that are on the order of 5 to 10 microns. And then the smallest level, these are hollow tubes with thicknesses on the order of 10 to 100 nanometers, which we can control pretty well. So this is a cut section. This is an octet truss hollow. Again, you have the size of the structure, the aspect ratio. Unfortunately, as a byproduct of the fabrication process, you end up with an elliptical cross section. So 2-photon lithography gives you an ellipsoid as your unit, which is not the end of the world, but it is what it is. You can build it up to make circular structures, but then you have larger features. The mechanics change slightly. I can talk more about that if anyone's interested. But there's a couple figures of merit for these materials that I'm going to point out now. So first is relative density. Anytime you're making a lightweight material, the amount of material in there, the volume of solid over the volume of the unit cell is the most important figure of merit. And from there, you can approximate certain mechanical properties. So certain things like stiffness and strength were theoretically said to scale with relative density. So it depends on what the constituent material is, and it depends on how much stuff is in there. So the relative density to some exponent. It turns out to be a little bit more complicated than that, which I'll get into, but that's the basic idea. So now I'm going to show a video. So this is our Alumina nanolattice. Alumina, remember, is a ceramic, brittle, catastrophic failure. If you compress it, think about compressing a coffee cup and what you would expect to happen, or dropping a coffee cup. It's kind of a brittle, catastrophic failure. So this, I'm going to say, is a thick-walled, thick here being 50 nanometers. So that's the length scale that we're working at as a frame of reference. And in compression, we get reasonably high strength, reasonably stiff performance, but brittle, catastrophic failure. So there's a single large strain burst, the whole structure crushes. It was pretty light, it was pretty strong. As an engineering material, those are useful properties, but if you imagine using this as a part of an airplane wing, you wouldn't want your airplane wing kind of catastrophically exploding in midair. So how do you get around that? So here we had taken that now, this Alumina octet, used the same architecture, the same material, the same geometry, the same everything, but now reduced it to be thin-walled. So here now this is 10 nanometers instead of 50 nanometers. And what we found, we kind of came upon this serendipitously. What we found in playing around in this parameter space was quite a different behavior. So now, instead of that catastrophic brittle failure, you can see this gradual ductile deformation up till about 50% compression, then we unload, 40% compression, then we unload. And actually it bounces almost all the way back. So some of these structures actually recover 98, 99% of their original height, which is pretty remarkable given what we had seen for the fully dense, or for the thicker walled structure. So what's happening here? So here we see this 10 nanometer one across all these different unit cell sizes actually was able to recover. There's a gradual transition as we increase that wall thickness from a ductile recoverable behavior to a catastrophic brittle behavior. And what fundamentally is happening is when you compress this thing, you have a hollow, thin shell that, if you imagine trying to crush a piece of paper, what's going to happen is that that piece of paper isn't going to fracture, it's going to wrinkle. So here we're actually seeing wrinkling or shell buckling in the shell, in the wall, this hollow ceramic wall. After we unload, we do see cracks form. There's some cracking that exists, which is why we don't see full recovery. But globally, the node remains intact, so the structure is able to recover. And there's no plasticity mechanisms because it's a brittle material. So it's either broken or it's not broken. And if it's not broken, it's able to bounce back, although it loses some of its integrity. So here we can determine a transition between those two behaviors. If you look now at a cross section in compression, you have regions of high tension and high compression. And in the, basically you have a competition between rupture in the areas of tension and buckling in the areas of compression. So you can relate those two. You can say either it's going to fracture or it's going to buckle, and we have a relationship for shell buckling. You can come up with a critical transition point, plug in some material properties, and say anything that's below that critical transition, i.e. our thin walled structures, will be shell buckling dominated and be able to recover. And so I'll come back to that a little bit later in the talk. We played around with hierarchical nanolattices too. So this was, I'm not going to go into this too much, just going to show it off because they're cool pictures. And there's a nice video that goes along with it. So here, this is a third order hierarchical structure. It's a lattice made of lattices. You can see the lattice subunit there, the lattice unit there, and then the lattice there. This idea we kind of took, again, here, a single order lattice. We made lattices out of those, lattices out of those. You can repeat this ad infinitum, and you can combine these across a whole bunch of different types of architectures. So it's a fairly general method. These at the top are CAD images. These at the bottom are SEM images. All the scale bars there are 20 microns. So again, we're getting the same sort of size and the same sort of complexity, or the same sort of size as the monolithic nanolattices, but an increased complexity in the architecture. So here, I'm going to show you cyclic compression on a third order half cell. Basically what we were looking for was how this hierarchy in a single beam changed behavior. So here you had a stiff, strong initial loading cycle. After that, you can actually see some of these cracks and voids starting to open up. So you can see, especially like here and here, cracked parts of the beam. I'm going to repeat that. Cracked parts of the beam stay cracked, and you have basically buckled pathways that form that reduce this initial peak load. But then you get to a pretty stable load cycle after just one or two cycles. So even though you lose a lot of that initial integrity, you're able to recover a bit better. So what this hierarchy buys you for this particular lattice is you were able to localize the failure more. So you're able to localize failure to discrete beams in the structure instead of parts of the shell wall, and that inevitably gives you better recoverability because more of the node or more of the beam stays intact. So I'm not going to dwell on that too much. Here, I'm going to pull us back to our property space. So you'll notice I extended this out quite a bit. Here's that density versus strength. You'll notice here at the top, so this yellow bubble is ceramics. Here, that ALD alumina, ALD AL203, this is the material that we were using. So it has yield strengths on the order of 2 gigapascals. It's much higher, especially in tension, than a normal bulk ceramic would be. And from that, so here now we can see this is where our monolithic lattices fell. So you can see if I drew a line up to that, this line would effectively intersect my ALD alumina. So we're getting higher strength, higher stiffness, or higher strength in this case, at the same density than normal foams. That's primarily driven because we're using a stronger constituent material. For the fractal lattices, we were actually able to get ultra low weights, which was interesting. So if you imagine cranes in construction, the reason we use cranes is because you can extend your size while reducing your weight. You wouldn't want a solid steel beam as a girder for a crane. So here, effectively what we're doing is creating a structure that mimics that. Interestingly, so as a frame of reference, the density of air is about 1.2 kilograms per meter cubed. So 1.2 kilograms per meter cubed. So we were actually making structures that were about a third or a quarter of the density of air. So that technically makes these air composites because air makes up a considerable fraction of the weight of them. Anyway, I won't dwell on that too much, just a fun fact. But here you'll notice if I draw that void line from my ALD AL203, that straight line, we're about a factor of 20 off from where we theoretically could be. So here we're getting good performance, we're getting ultra lightweight, we're reaching new property spaces, but we're still really not reaching into this white space the way we wanted to. So at this point, I had a question of why are we using lattices and what's the point of using lattices in these structures? So we went through a whole bunch of different types of lattices. Here's 4 that we ended up focusing on: octet truss, cube octahedron, Kagome, tetrachedecahedron, made lattices out of those. These have different connectivity at their nodes and theoretically are rigid, periodically rigid, or non-rigid. What that means is here, this octet truss, this is a pin jointed 2D version. This is fully triangulated. If I push on it, it doesn't move. This has no triangulation. If I push on it, it falls apart. And then the cube octahedron and the Kagome, basically anywhere those triangles are is a rigid element. And then you have periodic deformation around those in theory. So those are in principle supposed to scale linearly with relative density and quadratically with relative density. And this is kind of what all the lattice theories had told us, or at least that we were starting to go on. So when we look now at a property space, here's those 2 scaling lines. E is proportional to rho bar, E is proportional to rho bar squared. We actually didn't see that behavior at all. So if we look first at the octahedron, we see it's neither 2 nor 1 scaling, both for hollow and solid beam structures. For the cube octahedron, Kagome, and tetrachedecahedron, all of these actually collapsed onto each other very strangely. So it seemed at first glance that architecture had no role at all. So that all of these different lattice architectures, even though this was supposed to be stretching, this was supposed to be bending, actually didn't make a difference, which was somewhat off-putting. So we dug into it a bit more. And so here, these are our experimental parameters, or experimental values. We did corresponding numerical simulations to match those. And we found that basically in the relative density range that we were exploring, the beams themselves weren't the dominant factor that were controlling the mechanical properties. It was actually the nodes. So here, when you make very dense structures, the nodes take up a considerable volume fraction of your material, and you can't consider this as a beam-based structure. It's a combination of beam and node structure. And so when you get to very low relative densities, you actually get to that theoretical scaling that you're supposed to have, but here at high densities, you don't have that. And so in a practical sense, it's very difficult to make structures that are much lighter than 5-10% relative density, because you start ending up with them collapsing onto their self-weight. Any sort of imperfection can lead to catastrophic failures. And so this was a problem. So it seemed for a second that lattices weren't necessarily the way to go. Shell structures are supposed to scale more optimally. And so here, those are our shell results. We ran corresponding numerical simulations on matching parameters, and then we looked in a little bit more detail on different parameters. So here, those are our experiments. These are our matching parameters. When we started looking at different property spaces, we actually saw pretty drastic shifts in behavior. So there was actually awkward or odd transition points where at the same relative density, you could get an order of magnitude change in properties by changing exactly how the load was being carried by the shell. So here you have load concentration points, sharp corners. Here it gets to the point where it's just rounded out enough where you transfer the load differently in the shell wall, and you're able to drastically increase your performance. These were numerical simulations. We haven't actually done the corresponding experiments to validate these, but there's other reasons that we haven't, and I'm going to get into those a little bit later. Recoverability, I have 15 minutes left. I'll try to, so I have one more slide on stuff that I've done before, and then I'll get into stuff we're working on. So recoverability was the other big question. So there was a question of how do we make stuff lighter and stronger? How do we push this way in the relative density space or in the stiffness strength density space? But then there was also this other issue of recoverability. So we wanted to quantify the amount that these structures recovered. This is a Kagami lattice compression. We defined a figure of merit percent strain recovery, maximum minus residual strain. So if it recovers fully, then you have a percent strain of recovery of 100%. If it doesn't change at all, if E residual is equal to E max, then you have 0% strain recovery. And so, for example, this is 68% strain recovery. So we looked at polymer structures, and we didn't see, so polymer structures, you inherently have, so you can define a figure of merit lambda to define the slenderness of a beam. You can relate that to the buckling limit of the beam, and you can find a critical transition where you will go from an Euler buckling dominated to a yielding dominated behavior. And so you can see here the changes in qualitative changes in behavior, the sort of bursting event. These are Euler buckling events, and this is a densification and plastic yielding. But we found that slenderness of the structure didn't actually correlate very strongly to recovery, and more so the density loosely correlated with recovery, but even then there wasn't a strong trend, especially across all the different architectures that we looked at, which was interesting. When we looked at shell structures, so shell structures, you have again that T over A critical, that shell buckling versus yielding transition, where here this is a shell buckling dominated behavior, this is a yielding dominated behavior. And we saw that at that T over A critical transition, we saw that we were able to drastically increase our recovery. So it doesn't really depend on density, it doesn't really depend on slenderness. It very strongly depends on the aspect ratio of the shell wall. But we were still seeing structures that had a fairly low T over A that didn't really recover. So you notice there's a very wide spread, even when we get past this ratio, where some structures were and some structures weren't able to recover. So this was kind of a weird open problem. And this is one of the big things that I'll get back to. So that is basically most of the work that I had done during my PhD. I'm now going to give a bit of background, or I'm now going to get a bit into what we're actually working on now. So the problems that we've been trying to address, how we've been tackling them, what questions we're trying to answer. So one of the big questions that we had was, how do you increase specific strength and specific stiffness? So how do you go this way in our property space? We made these ultra lightweight materials. There's a lot of room to move up. How do you get there? And so shell structures, I'll get into in a couple slides, may not actually be the best way to do this. There's a different architecture that's actually more interesting, and that's called a tensegrity structure, or a tension integrity structure. This was coined by Buckminster Fuller, kind of an eccentric inventor back in the 1950s. But you have effectively isolated tension and isolated compression events. So if you design an architecture in a particular way, you can make it such that some elements in this only carry tension and some elements only carry compression. Now, in compression, elements can buckle, but in tension, they can't. You can't, oh, that's a, I'm not gonna get into that. You can have stuff buckle in tension, but that's a more complicated problem. Generally, for monolithic beams, you don't have things in tension buckle. And so here, you can make your tension elements much thinner and much lighter than your compression elements because you don't have to worry about them buckling. And all of a sudden, you can optimize the behavior of your material because you can drastically cut the weight of your tension elements and actually push yourself further into that lightweight material space. So they're naturally optimized for lightweight. Interestingly, we see tensegrities all over nature. So here, this is a cell cytoskeleton, this is the spine. In cells, the shape of the cell is actually dictated by the actin-myosin network. Inside of them, you have these actin tubules, myosin filaments that form a tensegrity network. So some are acting in tension, some are acting in compression, and it's that tension compression network that gives you the shape and the flexibility of a cell, combined with that phospholipid bilayer that gives you a protective membrane. In our bodies, your skeleton actually doesn't hold you up. If you just had a skeleton standing on its own, it would fall down. And it's actually the muscles, specifically the tension in the muscles, that form a tension compression network in your body. So this now, when you, if you didn't have muscles at all, so bones are thick and heavy and are primarily designed to act in compression, your muscles are designed to act in tension. And so that idea of this tension compression network naturally gives us an optimized lightweight structure. So in engineering, we see a couple examples that we've seen. These have been around since about the 1970s in the common vernacular. This is a nice structural example. This is a needle tower in Washington, D.C., where you get these kind of wild-looking art structures that stretch, I think this is 60 feet into the sky with something that it looks like nothing is holding it up. So it's kind of suspended there. This, in principle, is actually used in engineering a lot. For, say, for example, in suspension bridges. Suspension, you have the bridge itself and the main support columns acting in compression, and then the rods acting in tension. This is the Karipa Bridge in Australia, which is actually designed to look more like a tensegrity than a normal suspension bridge, so it looks cooler. And similar to the way the human body works, tensegrities are often used in deployable structures or actuatable structures, especially for space applications. So similar to the way we can move our bodies by changing the amount of tension in our muscles, we can change the shape of a structure by changing the tension or by changing the extension of different elements in there. What's most interesting about tensegrities is, for particular architectures, this is a simplex unit cell, you can change the mechanical response of that tensegrity by changing the amount of pre-stress in the beam. So if you create a structure that is loaded in a state of self-stress, so this one, you can change the stress in the rod without actually changing the shape. If you increase that tension, you can actually get stiffer or weaker responses. So weaker responses would be less tension, stiffer responses would be more tension in that element. And so we can use this idea of pretension to control the mechanical response of the structure. The problem is, actually there's one more fun example. This has been kind of floating around the internet lately. I don't know how many of you have seen it. These little Lego tensegrities, I think I saw somebody actually make a plate. These seemingly impossible structures that are supported by cables. Here, obviously, this can't support any compression. It's actually tension in these cables and tension in that cable that's counterbalanced by the weight of this. So it's the weight of it is pulling down there, that's creating this moment. Anyway, the big problem with tensegrities is that most of these have to be assembled by hand. So it's really difficult to actually make materials out of them. The other big question that we had was, how do you enhance a material's resilience? So you remember that these hollow structures are dominated by shell buckling. So you have wrinkling of the shell wall, you still have cracking that forms. And so we wanted to figure out how to get around this problem, how to make structures that wouldn't crack. And so we thought about, so this is inherently a buckling dominated process. You can think about this in the context of a soda can. If you can step on a soda can, it'll kind of buckle randomly and take on some random shape. It ends up getting sharp corners, sharp nodes. Those sharp corners will actually be failure nucleation points. You'll get kind of holes that start to pop in here, which is particularly bad if you want to then unbuckle it and reuse it. So how do you get around that? And one potential answer that we're looking into now is origami. So I have a student, Andrea Exel, that is working on this. If you take a sheet of paper and you apply boundary conditions and loads in just the right way, you actually get very ordered patterns. So this is an example of a Kressling structure. Kressling is an artist here who makes these types of origami structures. So we're looking at creating now nano-engineered shells. I'm going to make a quick point too about why we aren't actually going down the avenue of using shells to make lightweight structures. And it turns out, so this was some work by NASA in the 60s, when you have very thin shells, so this is basically as the aspect ratio of the shell is increasing, you have an empirical knockdown on the peak strength that shell can carry. So here our structures were in a relatively low aspect ratio regime, so that shell buckling formula that I had before, E over whatever the square root T over R, there's actually a gamma out front here that I conveniently ignored. And so this knockdown, this gamma, can drastically decrease your properties when you're making very thin shells. So you get a factor of 5, about a factor of 5 decrease in the load carrying capacity over what it theoretically can carry, which means that shells are highly sensitive to imperfections, which means if you want to make an ultra lightweight structure, you actually run into this problem very quickly because shells aren't optimal. But what we can do, another interesting avenue that we can look into with shells is controlling how they deform. So we're combining this idea of origami and buckling now. This is, again, some work that my student Andrea had been working on. We're creating these nano-engineered press-link beams or nano-engineered origami structures that we will eventually coat with a thin film of alumina, hollow out, and try to compress to see if we can engineer now the recoverability of a beam. Coincidentally, there's, for those of you familiar with work by J.K. Yang, he works a lot on origami beams. I don't know if he's actually in the talk. If he is, JK, you should talk to me about making nano origami. But his work actually focuses a lot on, or one of the interesting papers his that I've been drawn to recently is on memory in these. So you can create bistable states that these origamis can take on, which means we could, in principle, create a nano memory using nano-architected origami structures. In parallel, I'm running out of time. In parallel, I have another student, another postdoc who started working with me recently, Nishita, who's working on spinodally decomposed structures. So spinodal decomposition, actually a way around that cracking of the particularly the sharp corners of lattices is by creating rounded out structures. So there's a few groups who have been working on spinodally decomposed structures, which are semi-random smooth surfaces. Nishida is actually working on creating gradient structures, but with the specific interest in creating thermal shock resistance into these. So thermal shock resistance is the ability of a material to withstand large sudden changes in temperature. It's governed by the thermal expansion coefficient and either the strength or the toughness of the material normalized by the stiffness of it. It turns out when you're creating ultra lightweight materials, you actually get a benefit to your thermal shock resistance. So you can create very lightweight materials that have an increase in thermal shock resistance with decreased density. Coincidentally, conveniently, we can create ultra lightweight materials that have ultra low thermal conductivity. So we're looking at applications of these in thermal swing coatings, thermal shock or thermal barrier coatings, and kind of other high temperature applications where thermal shock is needed, thermal shock resistance is needed. Okay, technically at time, I have one more area that I want to talk through, and that's fracture toughness. So this is a fundamentally different area than I had looked into before, and I have a couple students now working on it, one in particular, Zainab Patel, working on how to create tough materials. So this is another Ashby plot, fracture toughness versus Young's modulus. Here you have stiff and tough materials. Here, which are metals and composites. Here you have technical ceramics, which are fairly stiff and strong, but really have a low toughness. So we wanted to see if we could engineer the toughness of a material. And to do that, we've started to look a lot into biological materials, tough biological materials. So this is a mantis shrimp claw. It has this kind of interesting woven boulagand architecture, kind of a twisted stack of fibers going along its length that change very depending on the position of the material. So we've looked at tough biological materials for inspiration for how to create tough nanoarchitectures. We're looking into the role of size effects. So fracture is a really complicated process that depends on the size of a crack, the sharpness of a crack, and the organization of materials in that crack or in the smallest phase. We can now actually engineer materials at all of these different length scales, or just about at this length scale. This one's a little bit tougher, but we can engineer materials across these different length scales to see if we can incorporate size effects into our materials. So using this idea now of statistical increases in strength, statistical changes in fracture mechanics to change the toughness of a material. And so from those tough biological materials, Zainab has been designing these micro fracture tests. So this, you can see we can create these sort of woven boulagand structures that qualitatively mimic that of biological materials. We can create micro 3-point bend specimens. Eventually, we're going to be working on pyrolyzing these to do 3-point bend tests. We still have a couple kinks to work out, but we're getting there. She's been making some good progress. In parallel to that, Nishita Anandan has been working on creating tough interfaces. So this has applications in, again, thermal barrier coatings, where you have large thermal gradients that cause these layers to crack and delaminate. So you have these cracks forming at these high temperature change interfaces. Here we're actually able to create sutured interfaces or nano-sutured interfaces where we can design different sorts of architectures at an interface to then create a thermally shock resistant material. And we can combine that with some of the ultra low K barriers that we were designing in parallel to create higher performance thermal barrier coatings. So with that, I wanted to thank everyone in my group who's been really doing a great job, especially in the very challenging situation that we've been in. I've been really impressed by their ability to keep pushing through despite everything that's going on. I've had a couple of great collaborators here. I actually didn't even talk about all of the work that we're working on. With Eric, we're working on some deployable biopsy tools. With Al Nelson, we're working on some 3D printable nano hydrogels. Marco and Vipin, we're starting to work on toughness of nanocellular foams. I have Rajiv Saigal in the neuroscience department, who we're trying to make needles with, or nano-engineered needles. Henry Lubati in physics, we're working on some carbon fiber composites. And then Emilio at Imperial University, trying to create hydrogen embrittlement resistant materials. So thanks to all of the people all the groups who have helped to fund this work. Some of the work that I'd shown was done at Caltech, but thanks especially to all of you here at UW for tuning into the talk, for giving me the chance to talk, for letting me come here. It's been a great experience so far. Yeah, a little bit more challenging in the last couple months. And with that, thanks, and I'm happy to take any questions.
I'm going to unmute everybody so we all can clap right now and applause. So I'm going to hit unmute for everybody, I think. Oh, sorry. I think everybody should be unmuted. I'm going to applause anyway, so there we go. There we go. Sporadic applause. There we go. There we go. Let's see. I'm going to go ahead and mute them all again. I was pushing the wrong buttons. I'll try that again next time at the end. But now we have time for questions from our audience.
Hi, Professor. This is Siam. I have a question. Is it possible to create nanoarchitecture on curved surface?
Sam, create nanoarchitecture on a curved surface?
Yes.
Yeah, you definitely can. And so there's a lot of, so with our methods, it's a 3D printer, we create arbitrarily curved structures, arbitrarily shaped structures, kind of in any organization. I think if you want to make things on a curved surface, there's different types of interesting architectures you can start to look at. So if you want to make like a core shell or like a beam plate sort of structure, there's a lot of like beetle wings that I've seen that have hyperboloids as the center supports of those. There's some interesting work that's been done recently by Thomas Sigmund on they find scutoid interlocks in the plates of a curved surface. So different ways that you can interlock surfaces to increase toughness. Specifically designed to contour to curved surfaces. Yeah, so there's a lot that you could do. The mechanics are in principle the same, but architectures shift a little bit around depending on exactly what you're looking to get.
Okay, thank you.
Svenja, you had a question. Do you want to go ahead and unmute yourself and ask?
Okay. Nate.
Go ahead, June.
Can I ask a question to Lucas?
Yeah, go ahead. Go ahead.
Very good talk, Lucas.
Thanks.
I'm excited to learn a lot of new activities in your group. Interesting that in the last few slides, actually on the current slide, the Boolean structure, is that you made recently? How did you make this structure?
So this was printed on the nanoscribe. So we had we've been making these. This has been some work by Zainab. We're creating beam structures that are supported initially by springs, so that we can eventually pyrolyze them and try to do a 3-point bend test. But these are just different passes of the laser path. So you can imagine, we can control exactly in 3 dimensions how the laser is moving. We have voxel level control. and voxel level all the way down to 150 nanometers, which is the spot size. So those are just line passes that she had been doing.
So it's the same material, just going through different passes.
Yeah.
Structure. Okay, I see.
And so right now, so eventually those will be pyrolyzed to create amorphous carbon. So it'll be a brittle material, and we're looking at ways to infiltrate that with a secondary material. So just the boule ligand alone isn't enough to dissipate enough energy, although we might get some interesting crack redirection. But really, you want a soft polymer phase to dissipate energy. So we're looking at CVD Parylene as kind of a first attempt whenever we're allowed to actually try things out again.
Okay, very good. Interesting. Thank you.
Yeah, thanks.
Other questions?
I don't know, am I unmuted?
Mhm.
Hi, Lucas, this is Cerise Jones.
Hey.
I'm here with my husband, actually, who has a question about your structures.
Yeah.
Okay, so hey Lucas, I actually have a degree in materials engineering, but I've done more protein stuff than like hard materials. But I guess my question is, do these kind of nanostructures, if you made them composites of like protein and brittle or something like that, like the mantis shrimp kind of structures are, do the equations change a lot when you're dealing with composites? Like there's a bunch of equations for how strength is distributed in composites. Is it significantly different on the nanoscale?
So yes and no. Stiffness wouldn't change too much. So just the elastic properties wouldn't change significantly. It'd be pretty much the same equations as you would have for normal carbon fiber or any fiber composite to the macro scale. Strength would change based on the constituent material. So strength just being when it starts to break, that would change theoretically because you would have a stronger constituent material that you'd be using. And so for different biomaterials get really interesting because it depends on the mineral phase and the organization of the architecture, the organization of the constituents, and it gets interesting and complicated. But at least the initial strength would primarily be limited by that strength of the constituent material. The toughness is where it gets really interesting, and that's where things change a lot. And there's not really good equations even for predicting the toughness of a material because it depends on what fracture mechanisms you have that are being activated. So it depends on whether you have fiber pullout, breakage, friction, interlocking, unwinding of polymer or of molecules. So something like spider silk, for example, is incredibly light and strong, but it's actually is a tensegrity, coincidentally, which I'm not going to talk about, but I'll throw that out there, has these beta pleated sheets that are stiff and allow this thing to stretch out to like, I don't know, whatever, 50, 60% strain to elongation despite being super, super strong. So the nonlinear behavior of biomaterials is particularly interesting. And that's the complexity. That's why I'm really interested in looking into toughness, because like strength and stiffness on their own are interesting and unique, but a little bit more predictable, whereas toughness, we're getting into entirely uncharted territory.
Would it be crazy to make a tensegrity of like brittle compressional parts and like spider silk as the tension parts, and then?
No, that would be perfect.
Just really hard to make.
Yeah.
You said that was for FCC metals. Is that true generally or only for those cases? And do we know why?
In general, this happens for different types of materials. So FCC, PCC, HCP generally holds. I think that size effect is more pronounced in FCC than other materials. I think part of the problem is HCP hasn't been studied as much because HCP is weird and complicated. And Julia's group had been getting into that when I was leaving. But yeah, when you have that prismatic slip versus basal slip versus whatever, it really depends on what orientation your structure is in, and that you get pretty drastic changes in strength because of that. But the mechanism for why these are why smaller is stronger is you have a statistical elimination of dislocations. So you have smaller things, so it's more likely to be single crystalline. And then you have a free surface where if you do have dislocations, they can escape out of. And so both of those still hold regardless of whether it's FCC, BCC, or HCP. As to then, so I think, well, first, does that answer your question?
Yeah, I think so. I mean, I was wondering if it was just a smaller likelihood of there being defects in there, and it sounds like that's part of it.
Yeah.
It seemed kind of counterintuitive that having a larger surface to volume ratio was beneficial, but in that regard, I guess it makes sense.
Yeah, basically you have like the atoms are free to move around on the surface, so you have lower strength. That doesn't really matter until you get to like 10-ish nanometers, which is also where you see size effects and stiffness coming in. So like the stiffness of these things doesn't really change at all until you get to about 10 nanometers. But so that surface effect is really predominant in polycrystalline materials, for example. So that's where you see that free surface really being detrimental. But yeah, the free surface here just serves to allow dislocations to escape. So you have a dislocation starvation mechanism, is what they call it.
Okay, thank you.
Yeah.
Well, Lucas, I got one small question.
Yeah.
Hello, by the way. Let's see.
Hey, good to see you.
I was wondering, because like you say you use carbon for the material that underlays the shell of the nanospheric. So so potentially you can use for some active material like piezo material, because some of these are like basically ceramics, and you can change the I guess like the electromechanical properties where you can like make them a sensor, not just like being a lightweight strong material. So I think that'd be really interesting. Yeah.
I like what you're thinking. Yeah, we've been talking to a professor in Barcelona, Irene Arias, about creating piezo and flexoelectric actuatable nano-architected materials. So she has worked a lot with piezoelectric and flexoelectric thin films, where flexoelectricity is based on the strain gradient instead of just the strain. So you can get an electric dielectric moment coming out even with non-piezoelectric material. Anyway, yeah, it's something we've been trying to get up off the ground. That's very much in my mind. I don't have a student to work on it yet, but if you wanna talk to me more, I'm happy to chat.
Oh, thank you.
All right. Well, I'm gonna unmute us all so we actually can say, give an applause. So here we go. All right, everybody give me that applause for you.
Sorry.
Thanks, everyone.
All right, thanks so much. And we'll go ahead and end it here.
Bye.
Yeah.
Bye.
All right.
Thank
See you later.
you.